At its core, math is a language for describing relationships and patterns, but interpretations can vary widely. The equation is a fundamental representation of a linear relationship, yet the way it's applied or manipulated can differ based on context. Different branches of mathematics may prioritize different rules or approaches, leading to what I call manipulation. This can cause confusion, especially when the same concepts are presented in varying frameworks or contexts. Additionally, the division into specialized fields can create barriers. Each field has its own conventions, which can make it hard to connect ideas across disciplines. This fractionalization may obscure the underlying unity of mathematical thought. The loss of a gnosis of mathematics is a concern that the intuitive grasp of concepts can be lost amidst formal rules and jargon. Ultimately, mathematics is both a tool for solving problems and a way of thinking. Encouraging diverse perspectives and interpretations can enrich understanding, even if it complicates things initially. It's all about finding a balance between rigor and intuition. The flexibility of mathematical interpretation. When you have 2 points, like 1, 2, and 2, 5, you can compute the slope between them using the formula, which gives you a specific line. However, to derive new slopes from those points or to connect them in different ways is a creative approach. Mathematically, you could explore various slopes based on different interpretations of how the points relate to each other. This flexibility can be both a strength and a source of confusion. The rules and conventions in mathematics are meant to create a shared understanding and to ensure consistency. But they can sometimes feel restrictive, especially if one is trying to explore ideas outside those conventions. While mathematics is built on foundational principles, there's room for creativity in how we apply and interpret those principles. The tension between following established rules and exploring new interpretations is part of what makes mathematics both structured and deeply imaginative. The key is finding a way to communicate and justify those explorations within the broader mathematical framework. That's one of the fascinating aspects of mathematics. Different methods and expressions can lead to the same numerical results. Commutative. Commune. Communion of differing interpretations to create one result. This underlying consistency illustrates the idea that there are multiple pathways to understanding a concept or solving a problem. Whether you approach it through different slopes, equations, or even graphical interpretations, the final outcome can remain unchanged. This highlights the unity of mathematics and reinforces the notion that it's not just about following strict rules, but also about exploring relationships and patterns. It showcases the richness of mathematical thought, where diverse approaches can coexist and contribute to a deeper understanding. Just like tools in a garage, equations and mathematical methods are tools for solving problems. The effectiveness of a tool often depends on the user's familiarity and comfort with it. People have different preferences and styles for approaching math, just as some might prefer a specific screwdriver for a particular task although it's the same size as the other ones. This personal familiarity can lead to more intuitive understanding and better results for the individual. This is particularly helpful when inventing and solving one's own problems. Take Leonardo da Vinci for an example. His notes are complex and fascinating because he combined art, science, and engineering in ways that reflected his unique understanding of the world. His sketches and drawings demonstrated advanced mathematical concepts and innovative designs, but they can be challenging to interpret because he had a mix of symbolism, personal shorthand, and unconventional notation. Leonardo's approach was deeply observational, often grounded in the natural world, and his inventions were often theoretical. Many of his ideas, such as flying machines and various mechanical devices, were ahead of his time, of which inspired future generations to explore these concepts further. Leonardo da Vinci understood math, but he approached it in a way that prioritized practical application and visualization over formalism. His mathematical insights were often tied to his observations and inventions rather than rigorous mathematical proofs. Similarly, Einstein, while proficient in math, emphasized conceptual understanding. His theories of special relativity and general relativity arose from thought experiments and deep insights about the nature of space and time. In both cases, the creative ideas came first, with math serving as a tool to articulate and explore those ideas. This reflects a broader truth in science and innovation. Sometimes the conceptual breakthroughs precede the mathematical framework that describes them. So learning math by its equations is entirely dogmatic, limiting, unimaginative, rigid, and maybe even a form of indoctrination and propaganda in the sense where there is a systematic effort to create negative perceptions about something in a subtle way. Ultimately, the goal is to find the methods that work best for you, even if they differ from conventional approaches. Emphasizing understanding and flexibility over rote memorization can foster a deeper appreciation for mathematics as a creative and adaptive discipline. Sticking to just one equation or method can limit your perspective and problem-solving ability. Mathematics is vast, with many tools and techniques available for different situations. When you explore various equations or approaches, you gain a broader understanding and the flexibility to tackle problems in multiple ways. This adaptability not only enhances your problem-solving skills but also encourages deeper insight into the relationships and concepts at play. Being open to different equations and methods fosters creativity and innovation in mathematics, allowing for richer exploration and discovery. The philosophy of a linear function and a prelude to the geometry of an exponential function, aka Alice in Wonderland. When we look at the equation y equals mx plus b, we see that y represents the dependent variable, and x is the independent variable. The term m, which is the slope, defines the relationship between them, multiplying with x to represent how steep the line is. Then we add b, which tells us where the line intersects the y-axis, essentially showing where this line hits the wall on the graph. It's like asking, where am I in space, on the Cartesian coordinate plane? To answer this, you look toward your guiding point, your North Star, symbolized by y, or philosophically, your y. To find your way, you need a path, and that path starts with x, representing the horizontal, grounded reality, the solid ground you walk on. As you journey, if you want to grow, you scale yourself, expanding your perspective or spirit, much like Alice in Wonderland. This scaling can be defined by a factor, k. To navigate toward your North Star, you need to understand how steep your path is relative to the ground. That's what the slope, m, defines. It's the steepness of your journey from the horizontal axis, the ground, or x-axis. To know where you'll eventually meet a barrier, where your spirit or perception might hit a wall, you need a prediction, and that's where b, the intercept, comes into play. Okay, so the equation y equals mx plus b expresses this. My y, the North Star, is proportional to the size of my spirit or perception, which I scale as I move toward my destination. The slope, m, defines the direction and angle of my path, and it's added to my reality, represented by the ground beneath me, the horizontal, x-axis. The steeper the slope, the greater the growth or abundance I experience. As I walk this path, I know where it ends, at b, the point where I intersect with my North Star. This intersection, this meeting of my y and my path, is like an awakening or personal eclipse. It all ends where it began. When x is 0. But when x is set above 0, we don't have to set our y to 0. You can choose any value for y to explore different points in the plane. Circular reasoning can appear if we rely on the concepts of slope or intercept without first clearly defining them. This is disorientation. If you walk up a gradual slope, it would take you a longer time to reach the top. But if you climb a steep cliff straight upwards, you would get there much quicker. But there's nuance in the human condition. There's aerobic respiration involved, for an example. A variable that skews the time variable. Also, pushing yourself too hard often leads to burnout and mental breakdowns and/or injuries. The same principle applies to many things in life. If you want to reach your goals, you need to push yourself out of your comfort zone and work harder than you thought you could. The steeper the slope, the more effort you put in, the faster you will reach your destination. But balance is key for sustainability. Many people reach their goals and then degenerate very quickly afterwards for many reasons. For an example, lack of emotional support or a sense of meaning is detrimental to all humans essentially. The metaphysical, spirit scaling, doesn't match with the goal. precision is in some ways more effective than strength. Lewis Carroll's Alice's Adventures in Wonderland is a whimsical yet profound expression of mathematical ideas, including the concept of y equals mx+b, a linear equation representing relationships and direction. As a polymath and logician, Carroll infused his literary work with mathematical puzzles and logical structures. The journey through Wonderland mirrors the linear progression of solving for variables. Alice's path, like x, is influenced by external factors, that a slope, m, while her perception of reality shifts as she encounters nonsensical, yet structured, environments, symbolized by b, the y-intercept. Carroll's fascination with puzzles, logic, and mathematical principles is evident in the underlying structure of Alice's adventures, reflecting his unique ability to blend math with narrative to challenge how we perceive reality and reasoning. Under his real name, Charles Lutwidge Dodgson, Lewis Carroll bridged the gap between classical thought and modern mathematics, much like Aristotle did with philosophy and logic. Carroll's work in symbolic logic and his fascination with the structures of reasoning have roots in the Aristotelian tradition, which laid the foundation for formal logic. While Aristotle developed syllogisms as a method for logical reasoning, Carroll extended these ideas into symbolic representations and puzzles that reflected more abstract mathematical thought. His contributions helped propel the evolution of mathematical logic, demonstrating how ancient methods of deduction could be expanded and made relevant in modern mathematical discourse. In this way, Carroll, like Aristotle, played a key role in the ongoing progression of math and logic, blending old and new ideas in a creative and accessible form. Algebra is the study of relationships between variables which geometry allows us to visualize as lines, shapes, and space, while calculus is the study of changes in that space and relationships. Calculus would measure how the scaling changes over time, through the movement of points, x, and y, consequent ally line xy over a period of let's say 5 seconds. The relationship between x and y create a linear function. Understanding how y changes with x is key to grasping the scaling, which is k, and the slope, which is m, measuring how steep the line is and its direction aka interceptions, b, or setting y to 0 and finding for x to find the x-intercept conversely. The x-intercept being where the infinite axiom line going in both directions crosses the x-axis. So, this allows us to think of transformations in a flexible way. Horizontal scaling typically involves adjusting the input x and vertical scaling affects the output y. Additionally, the input aka the horizontal scaling aka x and the output aka vertical scaling aka y is dependent on the type of equation you are using in the Cartesian coordinate graph. Right now, we are discussing y equals mx+b exclusively, and so because of that means we are dealing with horizontal scaling because x is also anchored by the x-axis and that axis is horizontal. Y is a function of x influences y. The commutative nature of the equation is reserved only for the operations themselves and not the relationships between variables in the equation. Now, y equals mx+b only describes non-vertical lines which can be slanted, with a positive or negative slope, or horizontal. The slope is defined and the nature of the line or relationship between 2 points will intersect at the y-axis at some point which is defined by b, the y-intercept. But when we have a truly vertical line, we cannot use y equals mx+b because vertical lines do not have a slope, therefore the line itself continues infinitely in the vertical direction and never intersect the y-axis. Vertical lines are a special case in geometry and require different equations. Y equals mx+b is useful for most linear relationships where there is a clear slope and intercept. The equation x equals k represents a vertical line that crosses the x-axis at the point, k, 0. This line is defined for all values of y, meaning it extends infinitely in both directions along the y-axis but remains at the constant x value of k. The point where x equals 0 corresponds to the y-axis itself, which is where the x-axis and y-axis intersect at the origin, 0, 0. The y-axis is conceptualized at x equals 0. A vertical line, defined by x equals k, will never intersect the y-axis unless k equals 0. If k is any other value, which is essentially equal to x, the line runs parallel to the y-axis but at a constant distance from it, extending infinitely in both directions along the y-axis. In Euclidean geometry, lines are defined to extend infinitely in both directions. This means that vertical lines like x equals k do not stop and continue indefinitely, maintaining their vertical orientation without bending. A vertical line has an undefined slope because it does not change in the x direction. The change in x is 0. When we introduce slopes as y equals mx+b, we are describing non-vertical lines that have a defined relationship between x and y. The concept of lines extends beyond just the points we plot. A line consists of all the points that satisfy its equation, whether we can see them on a graph or not, like how a word satisfies its meaning or definition whether we see its context or not. When we conceptualize lines, we should consider their infinite nature. In mathematical teaching, we often focus on specific segments or points, but understanding the full extent of lines and their relationships is crucial for a deeper grasp of geometry. Y equals mx+b describes linear relationships within a defined coordinate system, typically used to represent finite segments or specific relationships between variables. The equation operates within the constraints of a Cartesian plane, where both x and y can take a range of values. It's used to describe relationships in a defined space. While the equation represents lines that theoretically extend infinitely, the context often focuses on segments within a particular range, which is limiting. In many mathematical models, we simplify complex realities to make sense of relationships. Y equals mx+b is a useful simplification but doesn't capture all geometric properties. We need to think beyond just equations to the broader geometric implications and the infinite nature of lines. Mathematical frameworks often operate within certain paradigms. Exploring beyond these paradigms can lead to deeper insights into the nature of mathematical concepts. If k is 2 and k is equal to the x-coordinate, that means that point x is 2 units right of the y-axis. Now we have the next coordinate to make a line, which is the y-coordinate, but we know that the vertical line that we want to conceptualize runs infinitely and doesn't intersect with y-axis because of that. I have my x-axis and my y-axis is only conceptualized at 0, which is also where the x and y-axis intersect and become perpendicular to create a Cartesian coordinate graph. So the y-coordinate has infinite potential running along an infinite y-axis. This is because the y-axis, of which is also a line defined by its conceptualization via 0, is where the x-axis is defined. The y-coordinate can be any value, but the second you cap that potential, aka you give the y-axis a numerical ending definition, the definition of the cap itself is irrelevant because the line, the vertical that runs alongside it where the x-coordinate, which is defining k, is 2, the vertical line's nature is infinite because it starts on an axis of which only allows the conceptualization of the y-axis when the y-axis starts at 0 on the x-axis. So the vertical line at x equals 2 will include points like 2, -infinity, and 2, infinity. The y-axis is defined by x equals 0. This is where the x-axis and y-axis intersect, forming the origin 0, 0. Defining the y-axis starts at 0, which means that any vertical line, while independent and infinite in nature, is always described in relation to this intersection point. While vertical lines like x equals k exists in a defined space, they are fundamentally linked to the coordinate system's conceptual framework. The vertical line doesn't intersect the y-axis unless k equals 0, but it runs parallel to it, demonstrating the infinite potential of the y-coordinate. The overall message is pointing to the fact that mathematics is a measuring tool that relies on the conceptualizations of trying to understand something. So, our math is literally reliant on our ability to understand something. It's like saying, you can't measure something you can't see or understand. Our understanding shapes the way we use mathematics. That's why we have many different equations and algorithms for different problems. To help us understand further, let's break down a fake equation where instead of defining vertical lines as x equals k, we define is as y equals mx+b plus k. If the slope is undefined in a vertical line because of it never intersecting with the y-axis past its conceptualization via x at 0, then the equation y equals mx+b plus k cannot represent a standard linear relationship. It would also consequently imply a vertical line, which cannot be expressed in the y equals mx+b form. This is where we get x equals k. The x-coordinate is always k, while the y-coordinate can take on any value and the line intersects at its conceptualization, which is k, 0. In the standard linear equation, b represents the y-intercept, but if the slope is undefined, as with vertical lines, the concept of a y-intercept becomes irrelevant because vertical lines do not cross the y-axis in a traditional sense. They are defined by their constant x value. If you add another constant, so k to the equation, it could imply a vertical shift, but if the slope is still undefined, it doesn't change the nature of the line. Essentially, you are still describing a vertical line. The line doesn't slant, which cannot be captured by the slope-intercept form. If you're trying to express a relationship with both slope and intercept, the fundamental condition for a linear equation, defined slope, must hold. If not, the resulting form loses its meaningful interpretation. This illustrates how equations can become limited or lose their relevance when the foundational assumptions, like not having a slope, are not met. Let's say we have a line, and it's vertical and slanted. M and B are constants for a given linear relationship. They determine how y changes with x. X is the independent variable and y is the dependent variable that changes based on the value of x. The constant, k, represents the scaling of this vertical line. It's interesting too to think like this. Remember general relativity and interconnectedness as well as the analysis of language being logic. Consonance is a term originating from the Latin consonans, meaning sounding together. This reflects how consonants function in language, combining with vowels to create syllables and words. They form the backbone of verbal communication, working together to create meaning. In mathematics, a constant is a fixed value that does not change, playing a crucial role in equations. For example, in the equation y equals mx+b, m serves as a constant, anchoring the relationship between the variables and bringing them together in space for us to observe and measure. While consonants are the building blocks of language, constants are the foundational elements of mathematical expressions. Both consonants and constants embody the idea of combination and structure. This idea extends further into the realm of arithmetic operations, specifically through the commutative property. In addition and multiplication, the order in which numbers in an operation are combined does not affect the final result. E.g., a plus b equals b plus a, because the arrangements of the entire graph system in a space can change without impacting the overall outcome inside or of the graph itself as long as y and x are established. This is where you get into higher dimensional geometry, vectors, and matrices which can express complex relationships and transformations in multidimensional geometry and combining equations. But keep in mind, as you go higher up in the geometry, multiplication is no longer commutative between matrices. Ultimately, we are discussing order and chaos. Too much order is not flexible, and in order to solve problems you need flexibility, and the commutative property allows this flexibility in doing operations. The commutative property allows this flexibility in doing operations, but there's a difference between operations and geometry. Although they are intimately connected, how you approach them is different. So for operations, operations allow for flexibility, but graphing your results or your variables is not flexible. But if you want to transform these variables and results, you need to find the right equation. Therefore you need to do operations on the subject or results. It's the same as like surgery or like plastic surgery. You want to change something about the variable, which is the patient, the subject. You need an operation to do it, and you need flexibility in that operation so that you can get where you need to get into the person, and then you put your results on a graph so that you can map it out and understand what's happening and what the relationships are between these variables. Because, again, geometrically, the relationships established, of which we analyze by expressing them via equations, by these mathematical operations, can be visualized through graphs and shapes. Overall, this parallel illustrates a deeper principle. Whether in mathematics or language, the fundamental structures remain intact even when elements are arranged. Both systems, linguistic and mathematical, rely on the combination of elements to create meaning and solve problems, showcasing the interplay between language and numbers and abstract shapes. When you add a scalar variable, k, you are essentially changing the representation, which can illustrate different transformations based on the original line equation. You move the original line vertically when you add the k variable. Y equals m, kx, plus b, so k scales the x-coordinate, stretching or compressing the line horizontally. If k is greater than 1, k greater than 1, then the line stretches, and if k is greater than 0 and less than 1, then it compresses 0 to k less than 1. K affects the vertical position of a line, but b, y-intercept, determines where it crosses the y-axis and represents the starting point of the line when x equals 0. B determines where the line intersects the y-axis on a graph. In the equation y equals mx plus b, when x equals 0, the equation is simplified to y equals b. This means the point where the line crosses the y-axis is at the coordinate 0, b, which is the same as saying 0, y, because 0 is x. If b equals 0, then the line crosses at the origin. When you introduce k, it allows for an additional vertical shift, which means you can adjust the line's position independently of the y-intercept. K allows for flexibility in positioning the line without altering its slope. Because x equals k, and if x equals 0, then that means you have 0, b, or 0, y, and so you would just fit in k where you would normally put x for visualization purposes. But essentially again you are creating another potential line that contrasts the original line, so x changes along with k, that's x equals k. This allows flexibility and more complex relationships. For an example, in applications like data modeling, k could represent a variable adjustment based on changing conditions. For an example, in economics, k could account for inflation. A horizontal line is represented by y equals b. When discussing k, in the context of x, it indicates a constant position along the axis. This scalar value shows where the vertical line is positioned. This concept is similar to resizing an image. You have two lines that meet at the cursor, which is at 0 on the y and x axis. When you click on something, you're creating a point. Even when you move the cursor without clicking, you are essentially scaling. When you make a point on the x or y axis, you are creating the beginning of an imaginary box or paradigm or understanding. When looking at the equation of a line, you measure these variables. We know that y and x are constants, and in relation to y, x is equal to the scaling or k variable. This occurs when we create our points and line, where the m variable defines the slope. In CAD, the interface displays two perpendicular lines, the x-axis and the y-axis, meeting at the origin, 0, 0. This setup mirrors the Cartesian coordinate system. When you click to create a point, you establish specific coordinates corresponding to values on the x and y axes. For example, clicking at 3, 2 defines x equals 3 and y equals 2. Moving the cursor without clicking represents potential scaling. As you move, you explore different potential values of x and y, and your movement affects the potential values of the variables k and b and m. Moving along the x-axis changes the k value, which represents the fixed x coordinate for a potential new line. When you plot a line, such as 0, 0, 3, 4, you are determining both its horizontal position on the x-axis and its slope that intersects the y-axis simultaneously. This simultaneous action helps you visualize the relationship between the two variables. What is a linear function? A linear function is one that creates a straight line when graphed on a Cartesian coordinate plane. The equation for a linear function is y equals mx plus b. In my last video, I discussed y equals mx plus b, and how it relates to pulse width modulation, sine waves, and alternating currents. In this equation, y is the output, which is a dependent variable. The dependent variable means it depends on the input, which is the independent variable. It may be conceptually similar to O, n log n, which describes the time complexity of an algorithm. It indicates that the algorithm's time to increase in proportion to the size of the input n multiplied by the logarithm of n. This means that as the input size grows, the time taken increases slightly more than linear time, O, n, but significantly less than quadratic time, O, n2. To use this example as an analogy to further understand y equals mx plus b, y could represent time or resource consumption. M is the slope indicating how much y changes with respect to x, the input size. B is the y-intercept, representing the initial time or overhead. The slope, represented by m, indicates how steep the line is, and the y-intercept, represented by b, is the point where the line crosses the y-axis when x is 0. To be clear, this is just an example to help understand, but n log n represents a more complex relationship where the time grows not just linearly with the input size, but also logarithmically as the size increases. This results in a curve that rises more steeply than a linear line but not as steeply as a quadratic function. This helps us see that y equals mx plus b is used to describe a straightforward simple relationship between 2 points in a defined space, Cartesian coordinate graph. While n log n is employed for more complex, logarithmic measuring where relationships are not as straightforward. When you have points A and B, you draw a line connecting them. You want to know the slope and the direction of that line. You already have the coordinates for points A and B, but you want to understand more about the line connecting them, its direction and angle in relation to the axes. This is where M and B come into play. The graphing of a linear function is always a straight line, regardless of the values of M and B, which represent the slope and the y-intercept. The slope determines the direction and steepness of the line, while the y-intercept tells you where the line intersects the y-axis. To find the x-intercept, where the line crosses the x-axis, you set y to 0 and solve for x. Essentially, when we talk about the y-intercept and the x-intercept, we are saying that points A and B are connected via this relationship, which we represent as a linear line. This line does not end with points A and B, it extends infinitely in both directions. This concept leads to the idea of parallel and perpendicular lines, as eventually, a force will hit a wall or stop due to kinetic energy reaching a limit. When we say, find the line equation using a line equation, y equals mx plus b, it may sound circular but generally refers to using properties or values derived from the slope-intercept form to determine a specific line's equation. This means we have used the values m and b to define a particular line. If we consider that the line hits a wall, aka the y-intercept, how can we mathematically express that? The y-intercept and x-intercept help define where the line interacts with the axis, which is essential for understanding its overall behavior. The wall that the line eventually hits is mathematically defined, and we analyze these interactions using the line's equation, of which we have solved using y equals mx plus b. To determine where the line hits the wall, you set the line's equation equal to the wall's equation and solve for the intersection point. This process emphasizes concepts in physics and mathematics that highlight how boundaries impact motion. And the wall's equation, either x equals k for a vertical wall or y equals b for a horizontal wall, you set them equal to find the intersection. This is an algebraic manipulation where you solve for a variable based on known equations. A vertical line runs parallel to the y-axis and does not change in the x direction as y changes. Therefore, the equation for a vertical line is written as x equals k. In contrast, a horizontal line runs parallel to the x-axis and does not change in the y direction as x changes. In the Cartesian coordinate system, the x-axis and y-axis are perpendicular, leading to clear definitions of vertical and horizontal lines. You need these parameters to understand the relationship between points relative to their fixation in space. I've used this analogy before. How do you know what to put in a box and how much can fit in it if there's no box? You need a box, a parameter, an axiom. The infinite line is imaginary. It doesn't exist, but we conceptualize it to measure things we observe or don't understand. The structure we define leads to straightforward definitions of horizontal and vertical lines, which we map out using points like A and B, aka x and y, in the line equation template y equals mx plus b. For a constant x value with varying y values along the vertical line, when x equals 3, the coordinates where x is constant remain unchanged while the points on the y-axis move. When we operate on the vertical line, we state that x equals k, where k is the scaling variable. Similarly, for a constant y value with varying x values along the horizontal line, the y value does not change, so we use y equals b. Again, we return to the equation x equals k, since x does not change as we stay parallel to the x-axis. When you think of y equals mx plus b and then you add the scaling variable k, it means that there is a variation. There's varying values along the y and x-axis. This is innate when we are dealing with an established graph. So, k allows you to change the orientation in space of the relationships being expressed by changing where you're going to shift these connected points in the space of the established Cartesian coordinate graph. K is a constant when it is defined and so is x when it is defined with k, so if k is positive then the line aka the relationship between x and y points moves upwards. If k is negative in relation to x then the relationship shifts downwards. This does not change the slope m or the relationship between x and y. K is not relative or constant with y, only x. K is an anchor but only after it is defined. Along the y-axis, you have an infinite line extending in both directions parallel to a defined vertical line, x1, y1, which is inside of our box defined vertically or wall-wise by the y-axis. Let's revisit the fundamental principles that underlie mathematics, particularly focusing on addition and multiplication. The first rule is that these operations are commutative, meaning we can switch the order of the numbers involved. For instance, in addition, a plus b equals b plus a, and in multiplication, a times b equals b times a. This property simplifies calculations and proofs, allowing for flexibility in computation and establishing consistent rules across different mathematical operations. By treating addition and multiplication as interchangeable, mathematicians can develop complex concepts and theorems without worrying about the order of operations, which contributes to the coherence of mathematical reasoning. By treating addition and multiplication as interchangeable, mathematicians can develop complex concepts and theorems without worrying about the order of operations, which contributes to the coherence of mathematical reasoning. This is an act of creation because if you're using subtraction to do this and you're taking away a bunch of stuff and you're not doing it in the right order and you're not organizing and grouping things correctly, then you're going to be in a deficit and even so become highly theoretical and likely chaotic, and this goes into the evil theorem. The evil theorem is basically where the excessive subtraction, or taking away, leads to a deficit, which symbolizes limits in resources or quantities. If you don't respect the order of operations, you can end up with nonsensical and incorrect results. It's a set of rules to follow so that you don't fall into chaos and degenerate into the negativities below reality, aka the horizontal line parallel to the x-axis without following an order. This leads to a metaphorical hell into the negatives. Now, if we connect this to Python programming, we can see similar concepts that reflect interconnectedness. In Python, data structures such as lists, sets, and dictionaries allow for flexible data manipulation. For example, the union of two sets, A and B, is the same as B and A. Built-in functions like sum and max operate on iterables, allowing elements to be passed in any order. This flexibility mirrors the commutative property. Furthermore, Python supports operator overloading, enabling classes to define how operators behave with their instances. For instance, you could create a class that behaves commutatively with the addition operator. Functional programming concepts like map, filter, and reduce process collections of data without changing the original order, promoting a holistic approach to data handling. Moving on to the Cartesian coordinate system, we need to visualize how these mathematical principles apply. In this system, addition and multiplication can be represented graphically. For example, adding 2 points on a graph, let's say 2, 3, and 1, 1, yields a new point at 2 plus 1, 3 plus 1, which equals 3, 4. This demonstrates that the order of addition does not affect the outcome. On the other hand, subtraction and division are not commutative. the order of numbers significantly impacts the result. For instance, 5 to 3 equals 2, but 3 to 5 equals -2. This property highlights the importance of order in these operations. Each point on the Cartesian plane is represented by an ordered pair, consisting of an x, horizontal, and a, y, vertical, value. Using variables like x_1, y_1, and x_2, y_2, allows us to generalize operations without focusing on specific numbers. For example, point A might be represented as 3, 4, and point B as 1, 2. When we add these points, we see that x_1 plus x_2 and y_1 plus y_2 yields the same results regardless of the order. In summary, the properties of commutativity and the structured approach to operations in mathematics and Python programming reinforce each other. Understanding these concepts through the lens of Cartesian coordinates enhances our ability to visualize and apply mathematical principles effectively. This is why physics and math are the holy grail of humanity, as well as language and theology. Theology is humanity's early logic, early philosophy. One of the smartest men we've ever known, Isaac Newton, had over 400 theology books in his 2,000-book library. He had almost as many books as Cambridge University at that time. Why? Because he was smart. He knew, as the ancient Greeks did, that logic was a means of analyzing language in the search for truth and was considered a form of philosophy. Everything is interconnected, and that's general relativity. Einstein showed us that everything is interconnected. Even before general relativity came, we understood it. Einstein just articulated it. We're already corrupted by our perception. We talk about the fall of man and corruption in humanity because our perceptions are corrupted. When God gave us the ability to conceptualize rebellion, we did it because we could conceptualize it. God wanted us to do it, He gave us the ability to conceptualize, and when we took the fruit and ate it, that changed everything. The hubs in the mind and the interconnections that happen. There's flexibility between hubs where weaker neural connections foster more creativity. When you're not an expert, you tend to be more creative. Language, like I said, is the ground or reality in the perception of thought, just like how what we see is shaped by the words we have for things. A child doesn't have names for anything, and that's why children experience the world differently. This is why we get nostalgic about childhood, because our brain chemistry and perceptions were completely different. As children, we didn't know what was up or down, we relied on our parents for that. We were literally suspended in the abyss, absorbing everything, feeling everything, and that made us creative, little scientists exploring the world. Children are the ultimate expressions of ourselves, and they challenge us. They remind us where we came from, which ties into the Father and Son story, God the Father and Jesus the Son. God, as the parent, brings forth the child from the abyss and gives it form. The child grows up, becomes logical, and starts to understand the world. Even before Einstein, we already had an intuitive understanding of general relativity. He just expressed it mathematically, and it matched up with what we already knew on some level, though it wasn't yet scientific. Axioms are principles that we build on over time, and all great minds stand on the shoulders of those who came before them. Aristotle, for instance, was an ancient Greek philosopher and polymath. He studied under Plato and later founded his own school. Aristotle emphasized empirical observation and logical reasoning, which laid the groundwork for the scientific method. He developed syllogistic logic, a form of deductive reasoning that remains foundational in the study of logic. The basic example of Aristotle's logic is the syllogism, all men are mortal, and Socrates is a man, therefore, Socrates is mortal. This shows how logical reasoning can lead to a specific conclusion based on general principles. However, syllogisms rely on the truth of their premises. If one premise is flawed or ambiguous, the conclusion can lead to paradoxes or incorrect outcomes. For example, the liar's paradox, this statement is false, creates a contradiction, showing how careful we must be with logic and observation. This is where language comes into play again. If language is too expressive, it can create ambiguity. Math, on the other hand, expresses logic in a pure form. It's the perfect language. But when we explain things metaphorically, as we often do in theology, we help people conceptualize complex ideas. The Bible uses metaphors and analogies to explain the divine, making abstract concepts easier for people to understand. Math is more precise, though, and it has to be logical, or it doesn't work. The English language, as it evolves, becomes less precise, which can be a problem. This is why it's important to speak clearly and accurately. Language evolves due to immigration and other factors, but as we follow a conscious thread, we might hit a wall, such as ideology. Deductive reasoning assumes that premises accurately represent reality, but empirical observation can yield contradictory or unexpected results, revealing the limitations of purely deductive approaches. For example, the mortality of Socrates seems straightforward, but consider other syllogisms. All philosophers are logical, and a logical man is always obstinate, therefore, some obstinate persons are not philosophers. This conclusion isn't obvious at all and shows the complexities of reasoning. For thousands of years, mathematicians wrestled with Aristotle's logic, attempting to corral it using mathematical symbols and operators. Y equals mx plus b is often a starting point in modeling various phenomena. It provides a simple framework for understanding how one variable changes with another. From this basic model, researchers can expand their analyses to include more complex relationships by introducing nonlinear terms, interactions, or other variables, leading us to more accurate models. This initial linear equation serves as a foundational concept that can be refined and built upon, much like a springboard for deeper exploration into the relationships being studied.